Okay, in the last video, we discovered that e to the x is a function which is its own derivative. Okay, this fact right here is capital letters very special. And it's kind of unique. So I want to take a second to kind of explain this and talk about it. So there's this notion of what's called a differential equation, which is like an equation that says something about a derivative of a function and the function itself. So if we make an equation that says, let's say the derivative of y with respect to x equals y. This is essentially saying exactly what this is, right? This saying it's like the derivative of the function y equals y itself. Okay? If we set up this differential equation, then a solution to this would be a y equals f of x function type of thing, like a y that would satisfy this. And it turns out that the solution set, the set of all possible solutions, is just the set of all functions that are like a constant multiple of e to the x. So essentially what that's saying is this is not only is this a function whose derivative is itself, it's really the only function whose derivative itself, up to multiplying by a constant. That's the only thing you can do besides just take e to the x, is take e to the x times something else. So this is one of the things that makes the number e so special. Basically, it's like this curve, this y equals e to the x curve, is an amazing curve in that, like, at any point on this curve, the y coordinate of that point is also equal to the slope of the tangent line. So here at this point we have 0, 1, because e to the 0 equals 1, and this slope of the tangent line equals 1. Somewhere over here you might have this at height 2 or whatever, and at that point the slope of that line would equal 2. So it's a function whose value is equal to its rate of change. And that means that as it, I don't know why I drew it again. That means that, like, as it gets bigger, right, as the function's value increases, its rate of change is likewise increasing, which is the whole idea behind exponential growth, right? That, like, as the population increases, the rate at which it increases, and you can make it so that it's proportional. So changing the base of the exponential, like instead of e to the x, if you do 2 to the x, or 10 to the x, or like 1.05 to the x, changing that base turns out to be essentially like changing it so that instead of being the derivative is exactly equal to the function, it's some constant multiple of that function. And then you get this sort of idea of the rate of growth is proportional to the value of the function over, at any given time. Tons of cool applications for that beyond just population growth. You've also got like the other classic things we talk about, like exponential decay and like continuously compounded interest and that kind of stuff. So this is the cool calculus fact about the number e. All right, it is the only exponential base value that allows this exact behavior. And so then therefore it kind of becomes like the central focal point of exponential growth, and it is the sort of quintessential idea of the simplest type of exponential growth from which you build everything else. And it has the simplest derivative, and then we're going to base all our other exponential function derivatives on this one. So that's all I wanted to say about that.